first talk is going to be by Dr. Doug Cowen from the physics department, and he's going to tell us about recent detections of neutrinos.
Hey, first, thanks to the organizers for inviting me. And any minute now, my talk will appear on the screen here. Okay, so I'm going to tell you about searching for neutrinos in a very unusual environment and with a very unusual detector. So first I want to tell you about neutrinos. Some of you may have heard of them before. I want to introduce them to you. First of all, they're fundamental particles. There are 3 of the 12 fundamental particles in the standard model of particle physics. So there are 12 particles that make up all of the matter in the universe. And 3 of them are neutrinos. So they're shown here in this little picture, these 12 here. And the neutrinos are down at the bottom, partly because they are very light. In fact, we haven't been able to measure their mass. They also happen to be ubiquitous. In fact, I would say they're the very definition of ubiquity. I wonder if anyone knows or can estimate how many neutrinos per second are going through each of our thumbnails. And in order to sort of narrow this down a little bit, give me the exponent in the power of 10. Anybody?
8.
8. Too low. 50 is too high.
11.
11 is right. So 100 billion neutrinos are going through each of our thumbnails, and of course the rest of our bodies, every second. Even underneath the upper level of this restaurant, they're coming through. In fact, they're coming up underneath us as well, from below us. We are literally swimming in neutrinos. These neutrinos don't decay, as far as we know. And the good thing about them, in spite of the fact that they're ubiquitous, they do not interact with things. So it's a good thing that those 10 to 11 neutrinos go through your thumbnail every second and don't decide to stop there and bang into something. Because if they did, we'd all be dead. So neutrinos are extremely penetrating particles. They will go through us. They go through the Earth. They will go right through the sun. They basically don't care about anything that gets in their way, most of the time. Okay, so how do we detect these neutrinos if they're so incredibly antisocial when it comes to interacting with other bits of matter? The way we do it is by building a really, really large detector and hope that some tiny fraction of these neutrinos will actually interact. And it does work out to be the case that they'll do that. So when I say large, I don't know if people were here before we got started. There was some pictures shown of the Super Kamiokande neutrino detector in Japan. You saw a couple of guys floating around in a boat. I don't know if anybody saw that. It's a detector that's 40 meters high by 40 meters in diameter. It's huge. You could barely see the guys who were floating around in this boat. They were polishing photo tubes as the detector got filled up with water. So that detector is basically a little dot on this figure here, which shows the ice cube detector. The ice cube detector is a cubic kilometer of ice at the South Pole in Antarctica that we've instrumented by putting in modules into holes in the ice, which we melt using a hot water drill. These holes are nearly 2.5 kilometers deep. What we do is we melt these holes with a hot water drill, and then we pull the drill out. It takes about 24 hours to do that. Pull the drill out, and then we have this column of water left behind. And then we drop in a string that has 60 of these modules attached to it, and I brought one with me here that you can come up and ask me about afterwards. It's basically a bunch of electronics, and underneath, I don't know if you can see this, probably not, it has, here we go, what's called a photo tube, which is a device for detecting individual photons. And I'll tell you why that's important in a minute. So here's a picture of one of these photo tubes. Here's one going down into the ice. And we did this 86 times with a total of over 5,000 modules just like that. Then the ice, the holes, which are liquid, they refreeze, takes about 2 weeks, and then the detector is frozen in essentially forever or until global warming melts the ice cap. One or the other. Okay, so you might wonder if I've ever been to the South Pole. The answer is yes. Here's a picture of me there. This was taken in February of 2008. Most people who go to the South Pole usually go there between November and February. And then after February, the station closes and winter overs stay there. And no flights can go in or out because it's too cold. And the airplanes that land wouldn't be able to take off because their hydraulics would freeze. Towards the end of February, people like the guy pictured here start to get nervous about whether or not they're actually going to be able to leave the South Pole, because it starts to get a little bit cold. As you can see, I hope by this little placard I was holding, at the time I was holding that, that smile was frozen on my face. The wind chill was minus 73 Fahrenheit. So no one should ever complain to me about how cold the winter is here. Okay. So all these holes that we've drilled in the ice, there are big, thick cables coming out that connect each of those modules to the surface, and they're brought up here to this surface building. These strange structures on the left and right are where all the cables come up. And there are a bunch of computers inside here that take all the data that we see and try to figure out whether something interesting has happened, namely whether a neutrino has interacted or not. And I don't know if anyone can guess the nationality of the person who took this picture. There's a little hint up here. You see the flag that happens to be flying on top of. So the person who took this was Swedish. That's a Swedish flag that managed to be flying on top of the building. The IceCube collaboration consists of 40 institutions from about a dozen different countries, including Sweden. Okay, so how do we detect neutrinos with IceCube? We rely on something called Cherenkov radiation, which is what happens when a charged particle moves faster than the speed of light moves in a given medium. And you might think that's impossible because you've been told that nothing can move faster than light, but that's in vacuum. Light actually moves slower than that when it's in water or in ice. But there's no such restriction on a charged particle. A charged particle can move 99% of the speed of light in ice when light only moves at 3/4 the speed of light in vacuum. And when that happens, it emits what's called Cherenkov light. It's basically the electromagnetic equivalent of a sonic boom. And I have a picture of that happening right here. This is from the Brazil research reactor right on campus. And there's a video online that I took a snapshot from. And you see this blue glow. That's due to the electrons that are produced in the fission reactions inside the reactor going out into the water that surrounds the uranium, or whatever they use for their reactor, and going through the water faster than light moves, creating this blue light. So it's this Cherenkov light, this blue light, that we can detect when neutrinos bang into something in the ice at the South Pole. And let me show you what that looks like. So this picture here shows the individual modules. So each of those circles is one of these modules, like this one here, that has detected some light due to a neutrino interaction, which created a charged particle that screamed through the ice and emitted this Cherenkov light that was detected. The color of the circles is purely representative of the time at which the light was detected, the relative time, according to the colors of the rainbow. Red first, and then blue last. And the size of the individual circles represents how much light each of those modules saw. So if the charged particle went really close to a module, it would put a lot of light there. If not, not so much. But what you can see from this picture, I hope, is that this represents a particle that started out over here on your right and went over here to your left. That whole transit takes about 1/millionth of a second. 1 microsecond. And the other interesting thing to note is that this is basically going up in the detector. So you have to imagine yourself at the South Pole. Something going up through the detector means, if it's oriented like that it must have come from underneath the detector. The only particle that can do that, the only particle that's penetrating enough to do that, is a neutrino. So that's one way for us to identify neutrinos and not get confused by other particles, is by looking for particles that go up through our detector. Okay, so here is a video showing an event as it goes, a neutrino, as it goes through the detector. It bangs in over here on your right, bangs into something, causes a charged particle. It's called a muon, the charged particle it creates. And that muon then goes all the way across the detector. And you'll see it sort of in slow motion as it goes across, lighting up the modules as it goes. So here we go. So you see it starts over here and gradually makes its way across. Of course, this all happens in 1/1,000,000th of a second. These are the kind of events that we look for. Okay. So these events are huge. This is an example of one of the events, one of the first really high energy neutrino events that we detected. It produced light that extended over a range that was comparable to the size of the Eiffel Tower. Hundreds of meters in all directions. Now, IceCube detects 2,500 particles every second, mostly due to cosmic ray air showers that occur above the detector and send charged particles through the detector. These are almost all uninteresting to us. Astrophysical neutrinos, by contrast, arrive about once a month. So this is your classic needle in a haystack problem. The haystack, we were able to find these needles in the haystack by looking for really high energy events that were going up in the detector, and I show a few of them here. We discovered in IceCube these high energy astrophysical neutrinos and announced this discovery about 4 years ago. But at the time we made that announcement, we weren't able to say, it was a little bit embarrassing, where they were coming from. We couldn't identify any sources of these neutrinos. So then, several years later, we got lucky. It wasn't entirely luck. We planned for this. So an event, a neutrino, went through the detector, and it looked really good. So we immediately sent a signal to a satellite that transmitted the data from the South Pole to something called AMON at Penn State. Stands for, it's a mouthful, Astrophysical Multi-Messenger Observatory Network. Minutes later, that happened. So this is a very quick process. And then AMON sent out a signal, broadcast it worldwide to anybody who was willing to take a look in the same direction that IceCube thought the neutrino came from. And we got lucky. So the SWIFT satellite took a look and saw something there, but it wasn't convincing enough to make us sure that it was associated with the neutrino. But a different satellite called Fermi did see something. And once it announced something, which looked like this, so this is the bright spot in the middle, right near where the neutrino is. Once it said it saw something, something like 20 telescopes turned and took a look. And several other telescopes saw something interesting there. In the end, a counterpart was seen, and this kind of made neutrino astrophysicists feel sort of like Mega Millions winners. Months later, that had 994 authors because of all the people who were involved in following up this event, this neutrino. So what was that neutrino? So about 4 billion years ago, right around the time the Earth was forming, something called an active galactic nucleus, which is basically a really, really voracious black hole at the center of a rather unfortunate galaxy. It's sort of gobbling up the galaxy. Spits out a high-energy jet of particles. And that's kind of shown here. Right here in the center is the black hole. And there's this accretion disk of material and this jet that's coming out along the axis of the disk. That jet, it turns out, was pointed 4 billion years ago in just the right direction in order to intercept our planet 4 billion years later on September 22nd, 2017. And one of the particles from that jet was the neutrino that we detected. There were some high-energy photons that were also detected by a variety of other experiments. So this neutrino you could call the oldest particle from outer space ever detected, where when I say particle, I mean something that has mass. So photons that have been older have been detected, but photons are massless, not nearly as interesting as neutrinos. Don't forget that. Okay, so let me conclude then. So we have just witnessed the birth of high-energy neutrino astronomy. A brand new window on the universe has opened. We are convinced that there are other sources out there. So mapping the neutrino sky, which is what we'd like to do over the next decade or so with IceCube, can be accomplished in two different ways. One is to try to find more needles in the same haystack. And so we're coming up with better techniques for finding these neutrinos in the first place. And we're confident that we'll see more sources by doing that. Another option is to use a much bigger haystack. And so we are proposing to the National Science Foundation and its counterparts in Europe, in Japan, and in Australia to build a much larger version of IceCube, something like 10 times larger, in order to get even more of these neutrinos, to fully understand them. And I have listed down here, you probably can't read it if you want some more information about IceCube and other related experiments. And I also have some printouts here in case you want them. You can't read that. And lastly, if you're curious about this module and how it works, I'd be happy to answer your questions afterwards. Thanks very much. Let me just point out the IceCube collaboration is made up of all of these different institutions in all of these highlighted countries. Yeah.
After the detector is lowered into the ice, why does the ice freeze to be clear instead of opaque like the ice from our freezer?
That's an excellent question. Oh, sorry. So the question is, after the hole is melted and the modules are stuck in and the hole refreezes, why isn't the ice opaque after it freezes like the ice in your refrigerators, in your freezers? So the answer is, it is kind of opaque, and that's a major problem for us. It's not quite as opaque as you might fear, because I'm not sure exactly what makes ice cubes opaque. It's probably foreign material that's in the ice, in the water that freezes. The ice at the South Pole is very pure. So the problem that we have comes from bubbles freezing in rather than organic or inorganic matter. And those bubbles tend to scatter the light, so we still can detect it. It just gets its direction a little bit randomized, which is a problem. We have some ideas for how to improve that by changing the way we drill these holes so that not quite as much air is released as we're doing the drilling, and that way there won't be so many bubbles.
What's the field of view of the modules at question?
So the question is, what's the field of view of this module? So all these modules are pointing downward. So the question is, where can they detect light from? Which direction? So they're mostly sensitive to light that's coming upward, because all these modules, and the sensitive part is what you're seeing down here, are pointing downwards. However, as you heard in the earlier question, the column of melted and refrozen ice has a lot of bubbles in it, and so even light that comes down from above can easily bounce up into the module and be detected. So basically, because of the properties of the whole ice, that's the HOLE ice, the ice in the melted hole, because of the properties of that ice, this has a much bigger field of view than you might otherwise think.
Is there already a location that will be big enough to put the larger haystack?
So is there already a location that would be big enough for a larger haystack? There are in fact 2 known locations where this can be done. One of them is at the South Pole. There's plenty of space there. Nothing but space there. And the other possibility is in the Mediterranean. So there are groups in Europe that are trying to build a similar experiment, but in the water instead of in the ice. And there, for similar reasons, they have plenty of space. They could build a very large detector there, and they're working on it. It turns out to be harder to build a detector where the beach is 20 kilometers away than at the South Pole, where like the nearest Radio Shack is 5,000 kilometers away. Go figure. Stable platform on top of this ice shelf is a lot friendlier than having to do it from a pitching boat.
Right. Or they'd have to build a very rigid structure to put all that.
That's right. Yeah, it's tricky, and people have tried doing it for many, many years, and they may finally succeed in the Mediterranean.
Has anyone tried that on land?
On land, meaning
Drill the holes in through rock.
so if you drill the holes in rock, then you end up with a detector where the light can't propagate. So you can do that though with the radio. So people have thought about doing it in salt mines, because when neutrinos interact, they also produce radio pulses, and the radio can get through material like salt. So that is a possibility. But actually, they prefer the radio detector people to do it at the South Pole, because that way they can do it in conjunction with the existing ice cube detector. And that makes for nice coincidence studies.
Sure.
Yeah, so I was drinking more than listening, so I'm confused. So you were saying that could be flames of these coming out of our thumbs or through our thumbs.
There are. It's not that there could be.
So they seem very rare then when you're looking for them. Are they rare?
So
And my
neutrino.
follow-up question would be, if these things didn't exist, what would happen?
Okay. So they are not rare when they are low energy. So the ones that are going through your thumbnail 100 billion times a second are mostly neutrinos that are left over from the Big Bang, which will address your second question. The high energy neutrinos that we're looking for are much, much rarer than that. On the plus side, and the only reason that this science actually works, is that when they get to be really, really high energy, they are much more likely to interact. So they are easier to detect when they're at higher energy than when they're at low energy. Now to answer your second question, neutrinos were a necessity in order for the Big Bang to happen. Don't ask me exactly why, but they were. And they also played a role in helping form large-scale structure in the universe, which means galaxies and then smaller-scale structures that we care about, like planets. So without them, we wouldn't be here.
Is there any connection with Fermi-Lab neutrino experiments? If there,
So is there any connection with the Fermi-Lab neutrino experiments? Is that what you asked?
Yes.
Yes. So there is, but it's so indirect. So what I showed you here was one aspect of what the ice cube experiment can do, which is neutrino astrophysics, looking for high energy neutrinos and trying to locate their sources in outer space.
Right.
But the experiment also detects about 100,000 atmospheric neutrinos. These are neutrinos produced in the Earth's atmosphere. And it can use those to study something called neutrino oscillations. So these neutrinos come in 3 different types or flavors. And it turns out that they can change from one flavor to another as they propagate through space. In fact, 2 Nobel Prizes have been awarded for understanding of that particular phenomenon. And the ice cube experiment is able to do that measurement, and at Fermilab they're building experiments that are explicitly designed in order to make that kind of measurement. So IceCube is kind of a general purpose instrument, and we've determined that yes, we can make measurements of neutrino oscillations, and we're actually pretty competitive with what Fermilab can do with explicitly designed experiments. So we're proud of that, as maybe you can know.
This is kind of a follow-up to his question. There's another lab in Japan doing something similar to Fermilab, and I just saw recently they said they found a discrepancy between neutrino and anti-neutrino oscillations.
Right.
So but they didn't really specify how much of the matter asymmetry would that explain? Is it just a small part of it, or is it?
Okay, so if I could summarize the question. There's a similar lab to Fermilab in Japan. It's called, the experiment is called T to K. I'm forgetting what exactly that stands for. Tokai, I think, is where the accelerator is. And it sends a beam of neutrinos to the Kamiokande or Kamioka mine, in which the Kamiokande experiment is located. And that you saw at the beginning, before I got up here, the guys who were polishing the phototubes, they're in the detector that made the measurement that the gentleman just referred to. And what they recently announced is that they saw a discrepancy between the way that neutrinos and anti-neutrinos behave. So this has long been known in other sectors of the Standard Model, meaning quarks, for example, are known to behave differently if they're quarks or anti-quarks. This is called CP, which stands for charge parity violation. It means they behave differently if they're left-handed or if they're right-handed. Now, you cannot explain the fact that when the universe exploded at the Big Bang, there was a small difference between the amount of matter and the amount of antimatter that existed. So naively, not even naively, you would say that when something just explodes out of nothing, that it would create the same amount of matter as antimatter, and then you would expect that, as matter and antimatter tend to do, they would annihilate with one another and there'd be nothing left. Now, of course, we're all here, so that proves that that can't possibly be right. And what's surmised is that a tiny fraction of the matter, there was a tiny fraction more of the matter made than antimatter. You can't explain that tiny fraction by looking at the quarks and how they're different from one another, but you could explain it by looking at neutrinos. If neutrinos behave slightly differently from antineutrinos, that little difference could be enough to explain why there's more matter, or why the universe is matter-dominated and not antimatter dominated, or not equal amounts of matter and antimatter, in which case there'd be nothing. So this is a very important measurement. The measurement that they made is not statistically powerful enough to actually say something conclusive. In fact, there's going to be an experiment at Fermilab that's going to turn on in about 5 years that should be able to make this measurement definitively. And then we will know that answer.
Let's thank Doug one more time.
Thank you.